reflection and anti-reflection set of singular qualities.
Thank you. So, just a second. Okay. Okay. First of all, I would really like to thank the organizers for inviting me to give this talk. It's really a great pleasure. And then I would like to make sure that everyone can see the screen. Can you see the screen? Okay, and hear me. Do you no? Yet it is on. So okay, I should probably just put it up. Is it better now? Okay, great. Okay, so I would like to present a joint result with Yair Hayut, who also works at the Hebrew University. And this is about some principle of reflection together with a version of the square which are on the opposite, on the contrary, anti-reflection principle in a way. And so let me first explain you what I mean by principle of reflection or reflection principle. To me, a reflection statement is any a reflection property is any statement of the following form that says that given some structure that may be, I don't know, a set of ordinals or a non-theoretical object such as a group, a topological space, anything you like, and given some property of the structure, it is possible to find the substructure of smaller cardinality with the same property. So in other words, the property reflects to a smaller substructure. Now, Menachem will talk about compactness, which is dual to reflection, and the compactness principle to me is any statement that has this form, that given some structure, if every substructure of smaller cardinality satisfies a certain property, then the whole structure satisfies the same property. And this is obviously related to compactness theorem, actually, to generalizations of compactness theorem. So compactness is dual to reflection because when you have compactness for a certain property, you have reflection for the negation of the property. So I guess that Menachem's talk would be related to what I'm going to discuss. Now, you have already seen an example of a compactness property in ZFC, which is Koenig's lemma. So let me remind you that compactness or reflection property, Koenig's lemma, let me remind you, is the statement that says that if you have, let me draw a picture. If you have, so when you have a tree, an infinite tree, so a tree of height at least omega, with finitely branching, so it means that every level has size less than Aleph 0, less than omega, then the lemma says that you can find a cofinal branch through the tree. Well, V. I cheated here, this is not good. So let me think precisely. Sorry. Okay, never mind. So you can find a cofinal branch through the tree, namely a branch of an infinite branch, a branch of size Aleph 0. So you can see this as a compactness property because you can rephrase that as in the following way. Whenever you cut the tree, for every finite subtree of this tree, you can always find, if you cut the tree this way, for instance, you can always find a branch cofinal through the tree, the small tree, and so by compactness, you can find a branch which is cofinal to the whole tree, and this would be an infinite branch. Okay, so Koenig's lemma is an example of, and on the other hand, you can also see that as a reflection property, for the property of not having a cofinal branch. If the tree doesn't have a cofinal branch, then you should be able to find a subtree, a finite subtree that doesn't have a cofinal branch. But if the 8 is Aleph 0, then you are never in the situation where you don't find a cofinal branch through a finite subtree. Okay, so this is an example of a compactness property or reflection property that you have in ZFC. In ZFC, you can prove you can prove compactness properties, or you have reflection principles, reflection properties, or anti-reflection properties somehow. Sorry. This is an example of a compactness or reflection property. But we are interested in principles, reflection principles that are independent from ZFC. For those, we will see some examples of such principles. And for those principles, whether they hold or not, it really depends on the model we are working with. And in particular, reflection properties, they reflect a conflict between large cardinals axioms from on the one hand, and the axiom of constructibility V equals L on the other. In fact, large cardinals axioms, they typically imply reflection properties, while V equals L typically implies the failure of reflection principles, reflection properties. Okay, we can see an example of this. A typical example of a reflection principle is the reflection of stationary sets. For a regular cardinal kappa, we say that kappa has the reflection of stationary sets, and we denote it like this. If for every stationary subset of kappa, it is possible to find an ordinal alpha below kappa such that S intersection alpha is stationary in alpha. So, and we say that S reflects to alpha. So the reflection of stationary sets holds if for every stationary subset of kappa, every stationary subset of kappa reflects to an ordinal below kappa. This is an interesting principle to me. It has nice applications, and not just in set theory, but also in other areas of mathematics. So for instance, the reflection of stationary sets, it is equiconsistent with the statement that says that every kappa-free abelian group is kappa plus free, where kappa free means that every subgroup of size less than kappa is free. Okay, it's just to give you a taste of what you can do with such an abstract property. Now, for the reflection of stationary sets, this is the picture. In ZFC, you can prove that successors of regular cardinals do not have the reflection of stationary sets. So as I promised you, in ZFC you have both reflection and anti-reflection properties holding on. But for the other cardinals, it depends. Again, you have an example of how large cardinals and V equals L give you conflicting informations about reflection of stationary sets. And in fact, if we have if kappa is a weakly compact cardinals, for instance, then kappa does satisfy the reflection of stationary sets. So, and but also small cardinals can have the reflection of stationary sets. So, for instance, if you have assuming large cardinals assumptions, you can force a model in which Aleph omega plus 1 has the reflection of stationary sets. Okay, so large cardinals here, as I said, they give you they typically give you reflection properties. On the other hand, V equals L gives you anti-reflection, and here you can see it with the reflection of stationary sets. In fact, if V equals L, then the reflection of stationary sets fails basically everywhere but at weakly compact cardinals. Okay, so what next? So the result that I would like to present is about a strong version of the reflection of stationary sets, a much stronger version that we call delta reflection, and this appeared in a paper by Magidor and Shelah as a two-cardinal principle denoted delta kappa lambda, where kappa is less than lambda. So delta kappa lambda is the statement that says that whenever you have a stationary subset of lambda of points of cofinality less than kappa, whenever you have an algebra on lambda, namely any structure on lambda where you just consider less than kappa many operations, for instance, I don't know, you can take a group or anything you like, but you just need to take less than kappa many operations, then the principle tells you that you can find a subalgebra of order type below kappa, so a smaller subalgebra, such that S intersection the subalgebra A prime is stationary in the supremum of A prime. So let me rephrase this. If you have a stationary subset of lambda and a structure on lambda with few many operations, then the stationary set reflects to a subalgebra, to a small subalgebra of order type less than kappa. Okay. Now let's say that a cardinal lambda has the delta reflection when you have this principle, this property delta kappa lambda for every kappa below lambda. Okay, so this gives us an interesting principle to me, because this principle has many nice applications in several areas. It implies several compactness properties or reflection properties at once. So for start, it implies the reflection of stationary sets, but this is pretty obvious, and also it implies directly compactness for being free. So if you have an abelian group which is less than kappa free, well, first I said just kappa free. Anyway, it means that every subgroup of size less than kappa is free. Then if the group has size kappa, then it is free. Okay, and it implies other properties for structures of various kinds. They may be graphs, transversals, topological space with the property of being collection-wise Hausdorff. So for instance, for graphs, this principle, at kappa, it implies that if you have a graph of size kappa and every subgraph of size less than kappa has coloring number at most gamma less than kappa, then G has coloring number at most gamma. The coloring number is the least ordinal lambda, such that you have a well order on the graph, such that every point in the graph is connected to less than lambda many points preceding it in this well order. Anyway, this is just to give you just the taste of what you can do of the many things that you can do with this delta reflection principle. Okay, so once again, the delta reflection holds at weakly compact cardinals, just as the reflection of stationary sets, and but it can also hold at small cardinals. So, but not Aleph omega plus 1, unfortunately. Magidor and Shelah proved that assuming sufficiently large cardinals, you can force a model in which you have the delta reflection at Aleph omega square plus 1. And actually, Aleph omega square plus 1 is the least regular cardinal that can have the delta reflection. Okay. So this is a strong reflection principle that can hold also at small cardinals, and it implies several compactness or reflection properties at once. Now, my joint result with Yair concerns a version of the square. So square principles are anti-reflection principles. We will see why in a minute. But what are the square principles? These are the square principle was introduced by Jensen, and it's denoted like this: square index kappa. Square index kappa is the statement. It establishes the existence of a sequence of length kappa plus. So index kappa, the sequence is length kappa plus. So this is a sequence of clubs. For each alpha, C alpha is a club in alpha of order type at most kappa, so less than kappa plus. And the sequence coheres. That means that for every limit point of C alpha beta, C alpha intersection beta corresponds to C beta. It is exactly C beta. So let me draw a picture again. So the principle says that okay, here you have kappa plus. Now for every limit point alpha in or beta, yes, let's do like this. You have clubs through alpha and clubs through beta. And when you consider C alpha intersection beta, then this is exactly C beta. Okay, so this corresponds to this. Okay, so the delta reflection, it is incompatible with the square principle because okay, first let me say, why is this an anti-reflection principle? It implies the failure of several reflection properties, and for instance, it implies the failure of the reflection of stationary subsets of kappa plus. And so in particular, it is not surprising then that this principle, it is incompatible with certain large cardinals. If kappa is a strongly compact cardinal, then the square fails everywhere above kappa. And okay, so this is an anti-reflection principle. So since it implies the failure of the reflection of stationary sets, it also implies the failure of the delta reflection, because the reflection of stationary sets is a consequence of the delta reflection, as I said. Okay, but we will see that the delta reflection is compatible with a weaker version of the square. This version of the square denoted square parenthesis kappa, which is due to Todorsevich. And this is the following statement that says that there exists a sequence of length kappa. So again, a sequence of clubs. Each C alpha is a club in alpha, and the sequence coheres again. But this time, instead of requiring the C alpha to have order type less than kappa, we require, we have the following condition that says that there are no threads to the sequence, namely, there is no club in kappa such that for every limit point beta of C, C intersection beta equals C beta. In other words, there is no way to extend the sequence to kappa. There is no club C in kappa such that if you have this club to the sequence, then the whole sequence would still coheres. So this is square parenthesis kappa, and this is a weak version of Jensen square. Square kappa, square index kappa, it implies square parenthesis kappa plus. Okay. Okay, so this is also an anti-reflection principle. It does not imply the failure of the reflection stationary sets, but it implies the failure of the simultaneous reflection of stationary sets. Namely, it implies that there are two stationary subsets of kappa that do not reflect simultaneously, namely there is no alpha below kappa where such that they both reflect to alpha. And actually it also implies the failure of the simultaneous reflection in another version, namely that there are, if you have for every stationary subset of kappa, assuming this principle, you can split the stationary set into kappa many disjoint stationary sets that do not reflect simultaneously. Okay, so and once again, since it implies the failure of these properties, it is this version of the square is incompatible with certain large cardinals. So if you have a strongly compact cardinal, then also this version of the square fails everywhere above kappa. Okay, so here we have seen, what do we have next? Okay, so here we have seen a quite strong reflection principle, this delta reflection, and here we have also a quite strong anti-reflection principle, which is the square. So again, the delta reflection is incompatible with Jensen square, but I want to show you that. So our joint result with Hayut, it tells you that the delta reflection is yet compatible with this version of the square. Okay, before we go into the proof of this result, let me make some remarks about this. So this result tells us that that in particular the delta reflection does not imply the simultaneous reflection, because to Todorsevich square it implies the failure of the simultaneous reflection. So in any version you like, so in this model you have the failure of the simultaneous reflection, and so in particular the delta reflection does not imply the simultaneous reflection. And also, if you are familiar with the tree property, which is just the generalization of Koenig's lemma to uncountable cardinals, this is also another compactness or reflection principle. And Todorsevich square, it implies the failure of the tree property. And so in particular, in particular, the delta in this model you have the failure of the tree property at aleph omega square plus 1. And that means, again, that the delta reflection doesn't imply the tree property at aleph omega square plus 1. But this is actually something that Magidor and I already proved in another joint paper. So this is just another way to prove this fact, that the two principles are independent. So in general, this tells us that any reflection property that is refuted by Todorsevich square, it's not implied by the delta reflection. So the delta reflection is a quite strong reflection property, and yet there are some reflection properties that do not fall into the consequences of the delta reflection. And finally, so the delta reflection is incompatible with Jensen square, but it is also known to be incompatible with weak square. This is another weak version of the square. So this means that in a way our result is optimal, in the sense that you cannot find another. This gives us the strongest known version of the square that is compatible, that can be compatible with the delta reflection. Okay, so let's see. Yes.
So you're saying that weak square is stronger than the
No, none implies the other. I mean, neither the Todorsevich square implies weak square, nor weak square implies Todorsevich square. They are the picture is this. It's very simple actually. It's you have Jensen square, and this implies weak square, and it implies Todorsevich square for kappa plus, and this does not imply this, and this does not imply this. The two are independent, but the delta reflection is incompatible with this, and in particular with this, but it is compatible with this. So in this way, it is optimal. Okay. So okay. So let's go into the proof of this result. Of course, I will not give all the details. I will just outline the idea of the proof. So we want to force a model in which we have the delta reflection and Todorsevich square holding simultaneously at L omega square plus 1. So let's first see how do we get those two principles independently, individually. So to get the square is not that difficult. The forcing notion to get the square is you can force the square sequence with bounded approximations of the sequence. Namely, the conditions are sequences of clubs of length gamma plus 1 for a certain gamma less than lambda plus. So every C alpha is a club. The sequence coheres. And the conditions in this forcing are ordered by end extension. Okay, so if you force with this forcing, you get the square lambda plus sequence. Now, to get the delta reflection is more difficult. Yes. It's just the coherence. How do we know? Yes, yes. It's not hard to check that by the genericity you don't have a square a thread to the square sequence. Okay, so to get the delta reflection again is more difficult because it's a more complex principle. So the consistency of the delta reflection was established by Magidor and Shelah, and for Aleph omega square plus 1. And how do you get that? There is a key lemma that leads you to a model in which you have the delta reflection at L omega square plus 1. And the key lemma is this. If you have a limit of supercompact cardinals kappa n, let's say that lambda is this limit, then lambda plus has the delta reflection. So the idea is that you use this lemma to get the delta reflection at the successor of a singular cardinal, and then you want to transform lambda plus into Aleph omega square plus 1. Okay, so it's not difficult to prove this lemma. So we can go into the proof of this lemma. We fix so we get familiar with this delta reflection. Let's fix a stationary set and an algebra, as in the hypothesis of the delta reflection. So again, the ordinals in S have cofinality less than lambda, and the algebra has less than lambda many operations. So, but lambda is a limit of kappa n, so we can fix a natural number n large enough such that we can assume that the stationary sets, all the ordinals in the stationary sets have cofinality less than kappa n, and also the operations are less than kappa many. You have just less than kappa many operations. Okay, now we want to use the supercompactness of kappa n. So if you don't know what supercompact means, I'll give you just the definition. It says that no. So kappa is supercompact if for every gamma, there exists an elementary embedding of V into some M, such that the critical point of the embedding is kappa. That means that below kappa, J is the identity and kappa is the least ordinal, which is moved by J, and M is closed by sequences of length less than gamma, or at most gamma. And J of kappa is larger than gamma. Yes. Okay, so this is what supercompact means. Now we fixed an n such that kappa n is large enough for this to hold, and we want to use the supercompactness of kappa n. So we fix a supercompact embedding with critical point kappa n such that J of kappa n is larger than lambda plus, and all this property holds for gamma equals lambda plus. Okay. So now we look at the J image of the stationary set is a stationary set in J of lambda plus, and J of A is a larger algebra, is an algebra on J of lambda plus again that has, but still has less than kappa many operations, because kappa n is the critical point. So now we look at the pointwise image of lambda plus, and we look at the subalgebra B generated by this set, the subalgebra of J of A generated by this set. Now, since M is closed by less than lambda plus sequences, this set, the pointwise image of lambda plus, it belongs to M, and so in particular the subalgebra can be defined in M. Also, it's not difficult to see that the underlying set of B, it is precisely the pointwise image of lambda plus, and so the subalgebra has order type lambda plus, which is less than J of kappa. Now we look at J of S intersection B. I claim that this is I claim that J of S, the big stationary set, it reflects to this subalgebra, and in fact J of S intersection B, it corresponds to the pointwise image of S, and this is a stationary subset. It's easy to see that this is a stationary subset of the supremum of the pointwise image of lambda, so the supremum of B. So that means that M thinks that there exists a small subalgebra of J of A such that J of S reflects to this subalgebra. And so by elementarity you get the result in V, namely there exists a subalgebra of A with order type less than kappa such that S reflects on the supremum of X. Okay, so this was not too difficult to see, and this is a key lemma towards the construction of a model in which Aleph omega squared plus 1 has the delta reflection. Now, so how do we get the delta reflection at Aleph omega squared plus 1? Okay, so we start with infinitely many supercompact cardinals, kappa n, and so delta lambda plus has the delta reflection. And then we want to, again, to turn lambda plus into Aleph omega squared plus 1. So we want to add collapses. So this is quite technical, but if you're familiar with diagonal pre-reinforcing, it's not, the idea is not too complicated. So this is Magidor and Shelah. To prove this, they used they defined the forcing notion that we can denote P, which is analogous to diagonal pre-reinforcing. So for each kappa n, they fixed some normal ultrafilters on kappa n, and as this is typical, so let me write this down. For each n, you fix a normal ultrafilter on kappa n. So this ultrafilter actually it has some specific features, but it doesn't work with any ultrafilters. But anyway, you just fix a normal ultrafilter on kappa n, and then as this is typical for this is typical for pre-grid type forcing, the forcing adds an omega sequence through lambda, a sequence of all ordinals alpha n that are inaccessible in the ground model. So each alpha n is below kappa n minus 1 and kappa n. And then together with the omega sequence, you collapse cardinals in this way. So let's start, let's use the Israeli order. So let's start from right to left. So below kappa 0, what happens is the following. The forcing collapses cardinals between alpha 0 and omega 2. So alpha 0 becomes Aleph 3, and then it collapses all cardinals between alpha 0 plus omega plus 2 and kappa 0. So kappa 0 becomes Aleph omega plus 3, I guess. Anyway, and here you have you collapse all cardinals between kappa n plus plus and alpha n plus 1, and you collapse all cardinals between alpha n plus omega plus 2 and kappa n plus 1. So in the final model, each kappa n becomes an Aleph omega n plus something, and so lambda becomes Aleph omega square, and lambda plus becomes Aleph omega square plus 1. So here you can see that you need to leave gaps, and this is an important part. You need to leave gaps, and this is the reason why you have the property for Aleph omega square plus 1 and not for a smaller cardinal. You need to leave gaps because when you prove that the delta reflection holds in this model, you are in a situation, you find yourself in a situation in which the stationary set and the algebra, they essentially have size a certain Aleph n plus omega plus 1. And so this cardinal is here, and so if you collapse this cardinal, you damage the structure of the stationary set in the algebra, and you lose the property you want. So okay, so yeah, so more precisely, the conditions in this forcing are omega sequences. So the usual, yes, you're right. So here I wrote UN. Okay, so now the conditions in this forcing are omega sequence. So in the usual diagonal pre-grid forcing, what you have is the stem. So you have a finite sequence of ordinals alpha n that are each alpha n is an inaccessible cardinal in the ground model below kappa n, and then you have measure 1 sets, AI, etc. So this is, each one of these is in the corresponding ultrafilter UI. So this is diagonal pre-grid forcing. So it's divided into a condition. It has two parts: a finite part, which is called the stem, and the upper part. This is the stem, and this is the upper part. So the stem, it approximates the omega sequence that you're going to have in the final model, and the upper part, it selects condition for extending the stem, and this is made of measure 1 sets. Okay. Now in this forcing, the conditions, you have some additional components. You have the alpha i's, but you also have some functions, G0, F0, and then alpha n, Gn, Fn, and then you have An, some, again you have Gn plus 1 and some Fn, etc. Ai, Gi, Fi. Okay, so it still have two parts, the stem, the upper part. So the G part is responsible for collapsing cardinals in this lower part, and the F sequence is responsible for collapsing cardinals in the upper part. And these are not exactly measure one sets, but you can see them as measure one set that still select possibilities to extend the F sequence. And the GIs, so let me write precisely. You have each GN, it is in the collapse of alpha. So I messed up with the indexes usually, so let me, no, okay, so the GN is kappa n minus 1 plus plus less than alpha n, and Fn is in the forcing that collapses cardinals between alpha n plus omega plus 2 and kappa n. Sorry. And these are in the forcing that collapses cardinals between kappa I. So kappa I minus 1 plus plus and alpha, where alpha is any ordinal in AI. Okay, so if you want the exact definition, this is the exact definition of the forcing. And okay, so the important thing to say about this is that unlike Prickly type forcing, this forcing P, Magidor-Schellas forcing, it doesn't have the property that when you have two conditions with the same stem, they are compatible. Unfortunately, this doesn't hold for this forcing, essentially because the G sequence prevent the forcing from satisfying this property. Okay, so this is how you get the delta reflection at LF omega square plus 1. So we want the delta reflection and the square to hold simultaneously. Okay, so we know how to get the square individually, and we know how to get the square and the delta reflection individually, but to put them together, it's a different thing. So the main problem is that if you just first force the square sequence and then you would like to force with Magidor and Schellas forcing, but after you force the square sequence, the kappa n's are no longer super compact. So you cannot perform the same construction. Okay, so you lose the super compactness of the cardinals, but we can try to solve this problem by using this trick. So first, if we first force the square sequence at lambda plus will become Aleph omega square plus 1. Okay, so if you first force the square sequence at lambda plus, you do lose the super compactness of the cardinals. But if after this you thread the square sequence with a forcing that we can call T, then the super compactness of the cardinals can be resurrected. So if you assume that the super compact cardinals are indestructible by directed close forcing, there is a technique by Lever to do this. So you can assume that the super compact cardinals remain super compact after forcing with directed close forcing. Here you have that S iteration T, it is equivalent to a directed close forcing, and so in this model the super compactness of each kappa n it is resurrected somehow. Okay, and so you can use this to, here you can force with Magidor and Schellas forcing, and you would have the delta reflection at Aleph omega square plus 1. Okay, but now we lost the square sequence because we had a thread to the square sequence. So we would like to prove that t can be removed from the whole equation. Let's suppose that we were able to prove a sort of preservation lemma, something that tells us that if the delta reflection holds after forcing with t, then it already held before t. Okay? Then if we were able to prove this preservation lemma, we would have that in this model you have both the square sequence and the delta reflection, and we would have done. Unfortunately, life is not easy, and this doesn't work. So the reason why this doesn't work is that it's not possible to prove the preservation lemma in this way, because the threading force in T, it may destroy stationary sets. So it may happen that in S star P you don't have the delta reflection. There is some stationary sets that do not reflect, but then this stationary set, this bad stationary set, it is destroyed by T. And so after you force with T, you do have the delta reflection, but you didn't have it before. So you don't have the preservation lemma. So our solution was to make a preparation to force with an additional forcing R, an iteration R, that destroys all those bad stationary sets, all those sets that could be bad in S star P and then are destroyed by the threading forcing. So we destroy them in advance somehow. And okay, and now I can tell you more precisely how we define the forcing. So first we need to make an important remark about Magidor and Chelas forcing. Let's consider this product of collapses. Okay, so consider the product of all the collapses, the forcing that collapses cardinals between each kappa n plus plus and kappa n plus 1. And we call Cn this product starting from n. And so C0 is the full product. And in C0 you can define an equivalence relation on conditions. Namely, two conditions are equivalent if they are eventually equal. Namely, for some n, starting from some n, they take the same value. And let's say that the condition C is stronger, is less or equal star than C prime if C is eventually stronger than C prime. That means again that for some n, for every m greater or equal than n, you have this, that Cm is stronger than C prime m. Okay. Now, given this equivalence relation and this ordering less or equal star, let's call C finite the forcing given by the equivalence class ordered by this ordering. Okay. Now, this is important because the Magidor and Chelas forcing can be seen as an iteration of C finite followed by another forcing P star, which is the same forcing where the G sequence, it belongs to the generic for C finite. So the advantage of looking at the forcing in this way is that in P star you do have the property that two conditions with the same stem are compatible, and this is important. It's very useful in the proof. So given this fact, let's see how do we define the final model. Okay, the idea is that we want to we take this factorization, and instead of forcing the square and then doing the Magidor and Chelas forcing, we just force the square together with the C finite part, and then we just take aside the last part of the forcing, the P star, and we do it later. So first we force with this, and then we do the preparation. So again, this is an iteration, and it is such that it is defined in such a way that if you have a stationary set in this model, then its stationarity is generically preserved. Namely, the maximal condition of T still forces that the stationary set, it remains stationary. So that means that you can find a generic for the thread enforcing in which the stationary set is still stationary. Okay. Now, so R is this iteration, this preparation. Now, we observe again that if we take the expanded, so if we force with Cn, so not C finite but Cn, and the square sequence and the preparation and the thread enforcing, then this is equivalent to a directly closed forcing, and so so kappa n is super compact in this model. Okay. Now, so in this model you can find a normal ultrafilter on P kappa n lambda plus. This has a natural projection to a normal ultrafilter un on kappa n, and now you can use you can prove by the distributivity of the closure of the forcing, you can prove that this ultrafilter actually already existed in V. So you can use these ultrafilters in V to define Magidor-Enchelas forcing. And now the final model, it is the following. You have C finite, the square sequence, and then you have the preparation, and finally you have the P star of this forcing. Okay. Okay, so why does it work? We have to prove that we have the square sequence, that we have the square and the delta reflection in this model. So the square is, to get the square is easier. So the square, the forcing S, it adds a square sequence. So you do have a square sequence after you force with S. And then you just have to prove that the other components did not affect the square sequence, and it's actually quite difficult to damage a square sequence, because if you have any forcing B such that B times B doesn't change the cofinality of lambda plus, then you don't add a thread to the square sequence. Okay, and the other components of our forcing, they do have this property, so in the final model you still have the square sequence. Okay, so this is for the square. The delta reflection, it is more difficult. The proof takes like 10 pages, and I wanted to fit everything in one slide. So I will have to make some oversimplification, but it's just to give you the idea. So suppose you have, so you consider a stationary set and an algebra in the final model. Now we step back to the model before we force with P star. So we step back to this model. In this model, the stationary set and the algebra, they don't exist, but they kind of have. You can define some fake versions of them. You can define a fake version of the stationary set and the fake version of the algebra, and we can call them S star and A star respectively. And now this fake version of the stationary set is still a stationary set. It is a stationary set in this model. But we defined the forcing R conveniently in such a way that whenever you have a stationary set like this in this model, then you can find some generic extension for the threading forcing in which the stationary set remains stationary. This is how we use the trick. So in this model, S star, it is still stationary. Okay. Now we want to use, so suppose that here we can assume that we can fix some n large enough such that every ordinal is S cofinality less than kappa n. All the relevant objects are below kappa n, and it is still the case for the fake versions. So we want to use the supercompactness of kappa n, but kappa n is not supercompact in this model. It is supercompact in this expansion of this model when we force with in a Cn followed by the rest. Okay, so if we force with Cn quotient C finite, then we can see that quite easily that S star, it is still stationary, and here the advantage is that here kappa n, it is supercompact, and we can use the same argument of the key lemma to get a subalgebra B star of the fake algebra that has order type less than kappa n, in which the fake stationary set reflects. Okay, so you have this subalgebra, this fake subalgebra B star. Now, okay, we are still working with T, but now T can be removed. Namely, by the threading forcing, it is distributive enough so that the subalgebra B star it already existed in this model. And so we have a fake subalgebra where the fake stationary set reflects in this model, and all the objects, all the fake versions are defined conveniently in such a way that this gives us, in the final model, a subalgebra of the real algebra such that the real stationary set reflects to it. And so we have our result. Okay, so I hope this was not too technical. I hope that I explained clearly enough the idea of the proof, and in any case I thank you for your attention.
Thank you very much. Any questions, any comments? Can you say anything about this fake stationary set? Name, or what is it?
It's essentially, okay, for the fake stationary sets, it's essentially those ordinals alpha in lambda plus such that some condition in P star forces it to be in the real stationary set. So essentially you fold into, you take into account the conditions of the forcing P star, and you can prove that this is still stationary and everything works.
Okay, if there are no further questions, let's thank Kawa again.